I'm Neil Johnson of AgileSOC.com. A couple of weeks ago, I did a post talking about how SVUnit usage has grown the last couple of years, and that is great, but also that I felt like I was ignoring a full half of the audience I intended to support with SVUnit, which is pretty much the entire design community. SVUnit is really catching on with verification engineers, but I don't feel like it's catching on with design engineers like I had hoped. And in that post, I said I'd try and change that by shifting focus back to what I could do for design engineers, and this video is the start of that. So this is like an SVUnit 101 type video specifically to help designers jump through the first few hoops with respect to SVUnit. So we'll look at how to build a unit test template for a module in your design. We'll look at how you can set up file lists and file dependencies. We will write our first unit tests around some combinational logic in our unit under test, and we'll also write a couple of unit tests for some synchronous logic in our unit under test. And for our design or our unit under test, it is a module called RTL, and it is a very simple module. As you can see, it's basically an AND gate and a flip-flop. So we're going to write tests to make sure that the output of that AND gate and the output of that flip-flop are functioning as we expect. So let's get started. Now the first thing we're going to look at, we'll just take a quick look at the design. So our design is in this file called rtl.v. You can see it's a Verilog module, simple module. We've got clock and reset inputs. We've got inputs A and B. Those are the two inputs to the AND gate. And then we've got the asynchronous and synchronous outputs called AB and then QAB. That's our I/O. As is commonly the case, this is a hierarchical design. So part of the functionality is contained in this module called myAnd module. So we've got connections there. And then we've got the always block for the QAB. Now if we look at myAnd module, it is pretty much as you would expect. Oh, we've got two inputs and one output, and this is our AND gate here. So that is our entire design. Now, if you have a design that you want to write unit tests for, the first thing that we're going to do is we're going to create a unit test template. And we're going to do that by calling a script called createunittest.pl, and we're going to have rtl.v be our input to that script. We'll run that, and we'll see that the output of that is this file called rtl_unit_test.sv. This is what we're going to look at now. We'll just take a look at what comes out of that. This is just a bare bones template. And the thing that we're concerned with right now is this is a template that makes an instance of our module called RTL, and the instance of that is called myRTL. Now the first handy thing that SVUnit helps us do is just see that our design compiles. So before we write any tests, before we do anything, we're just going to try and compile. We're going to try and run this unit test template just with the RTL instantiated and nothing more. So we do that by calling a script called run SVUnit, and we have to specify a simulator. It doesn't matter which simulator you specify. You can use VCS, you can use Questa, you can use Incisive, you can use Riviera Pro. SVUnit supports all of those. For this demo, we're going to use Questa. So we're going to compile and run that test case template by invoking run svunit-s Questa. We'll see what happens. Okay, we've got some errors here. And these errors are typically what you'll see when you're starting a new set of unit tests for a Verilog module. And the first common thing here is that our Verilog module includes a file called defines.vh. Now, in a defines file, there might be some other tick defines, there might be timescales, there might be any number of things. For us, it ends up being a tick define called width. SVUnit can't find, or Questa can't find that, and the reason that it can't find it is because we have to, it doesn't know where to look. Now if we look back at our design, we can see right on line 1 here, this is where defines.vh is being included. But in order for Questa to know where to look for that, we have got to add an include dir. And we're going to do that in a file called svunit.f. This is a standard Verilog file list that pretty much every simulator in existence is going to be able to understand. And inside that svunit.f, we are going to add an incdir, a plus incdir plus dot sum lib dir. This is where that file is included. Now, for a real design, this might be some directory somewhere else on the file system. It might be some IP directory. It could be somewhere totally different. For us, it's local. But the important thing here is if you've got some files that are being included inside the svunit.f file list, you're going to have to specify where those include files come from. So let's run SVUnit again and see what happens now that we've included the proper directory for our defines.vh. Okay, so now you can see we got past the compile error that we had before, but now we are on to our second, what's going to be a common error you're going to see during compilation. And that is we've got this extra module called myAndModule. The simulator can't find that. And that's because we don't tell the simulator about that myAndModule. So that's what we're going to do now. We're going to go back into our file list, our svunit.f, and we are going to tell the simulator that myAndModule is a Verilog file that needs to be compiled as part of the simulation. So let's see what happens when we run SVUnit now. Okay, now we have a compiling design. We don't have any unit tests running yet. We have a compiling design. And again, to do that, our design was including a file. We had to set up an incdir for that, and we did that in svunit.f. And then there was another module that was required in our design as well. There was another instance of myAndModule, and we also had to set that up in our svunit.f, pardon me. So standard Verilog file list, we've got incdirs, we've got other modules that our design requires. Now we've got a running simulation. And in the output here, you can see, really this is an important line. You can see that 0 of 0 tests are passing, which means we have no unit tests running. And now we are going to take the step toward getting a unit test going. So let's go back into RTL unit test. Now the next thing that we're going to have to do is, because we want to be able to drive inputs and sample outputs of myRTL. In order to do that, we have to connect the I/O. So that's something that we're going to insert here right on after line 14. We've got the instantiation on line 15, but we want to connect the I/O. So we are going to do that by declaring regs for A and B. These are our inputs. And then we're going to have some wires called AB and QAB. These are our outputs. And then we're going to connect these to our instantiation. So A, we're going to connect to A. B, we're going to connect to B. AB is going to connect to AB. And QAB is going to connect to QAB. So now we've got an instantiation. We also have all the connectivity that we need to be able to drive inputs. We're driving inputs with reges, and we've got what we need to sample outputs, and those are wires that we've connected. So now, just to make sure that we've done that correctly, we're going to close this, and we're going to run the sim again, and we're going to hope that this compiles and again runs as we saw before. So let's just make sure we haven't injected any errors here. Yep, compiles fine, runs fine. So it looks like we at least haven't made any syntax errors in the connectivity. So now let's go, and we're going to go and write a unit test now. And there's a lot of code in this template. We're going to ignore all of this for now, and we're going to jump down to these two macros on line 62 and 66. All of the unit tests that we write in this unit test template are going to come between these two macros. And the first test we're going to write is we're going to make sure that our AND gate is working as we expect. So we're going to write an SV test called AB output is 1. And the end macro is called svtest end. So every test that you write in the test template is going to start with an svtest. It's going to have a string identifier for the test. That's the beginning, and then it's going to end on, like on 66 with a tick svtest end. Now between here we're going to write a test, and we're going to set both of our inputs to 1, and then we're going to make sure that the asynchronous output of our myRTL is also going to be 1. That's the functionality of the AND gate. So our A input we're going to assign to 1. Our B input we're also going to assign to 1. And then we're going to use a macro called fail if AB, that is our output, is not equal to 1. That's what we are expecting. Now the reason why I use a not equal here is just to make sure that if we get an X out, we want to make sure that we get exactly 1, not an X, and so that's why we use a not equal. Now one other thing that we need to do in here is, because this is asynchronous logic, we're setting inputs and we're immediately checking the outputs. In order for the output to reach or to actually be resolved, we need to wait. We need to wait for the inputs to propagate to the outputs. To do that, we're going to set a 0 time delay here. A simple #0. This allows the inputs to propagate to the outputs such that this fail if assert on line 70, this is going to be checking the asynchronous output AB after the inputs have time to propagate to the output. So this is our first unit test, basically checking the functionality of an AND gate. Very simple. We're going to go back and we're going to run this test and see what happens. Now here we're expecting one of one test passing, because we're pretty confident that our AND gate is coded correctly. And that's what we've got here. So we have got in our log file now, we've got an AB output is 1 test. We can see it's running. We can see our AB output is 1 test has passed. And we can see that we've got 1 of 1 test passing. So this is success for us. We have our first unit test running. We know that our AND gate, at least when you put 2 1s in it, our AND gate is working properly. So let's go back and add another test. Now we want to make sure, we're going to add another test here. We're going to make sure that if we don't have 1 and 1 going in, we want to make sure that we can get a 0 out of that AND gate as well. So we're going to copy this test. Oh. We're going to paste it. Whoops, pasted it into the wrong spot there. We're going to paste it down. Now we're going to have a test called AB output is 0. And we're going to put 1, 0. We're going to put a 0 and a 1 as inputs to the AND gate. So we're going to set A to 0. We're going to have B equals 1. We're going to have that 0 time delay again to have the output resolve. And then we're going to have to fail if AB is not equal to 0 this time. And I made a copy paste error here. I need to put the finishing macro on my unit test, the SV test end. So here's another unit test. Now we've got two. We've got two testing a true output to the AND gate and a false output. So we can run this now, and we're hoping for 2 passing unit tests now. And that's what we've got. So now we've got an output is 1 test, that's passing. And we've got an AB output is 0, that's passing as well. Now we've got 2 of 2 tests passing. Yeah, at this point, I think it's pretty fair to say that our AND gate is working as we expect. But that was only half of our design. There's also the flip-flop in there. We want to make sure that the output of the AND gate is connected to that flop properly. So now, in order to test the synchronous logic, we need a clock. Now I've just added some clock and reset utilities to the SVUnit release package. And we're going to include those utilities by doing a tick include of something called clock and reset.svh. This is a simple clock and reset utility. Now, like before, when the simulator couldn't find our defines.vh, the simulator is also not going to be able to find this clock and reset yet because it doesn't know a path to it. So we're going to close this. We're going to go back to our svunit.f. We're going to add another include-dir here. Incdir plus, this is going to be one called svunit install /svunit_base/util. So that file that we just included in our unit test template, that's in a util directory in the SVUnit install. And you can take a look at that if you like. Very simple utilities in there. So now going back to our unit test template, we have the clock and reset file included. We have the plus incdir in our file list, so it's going to be able to find and compile that. You know what, let's just make sure that that's the case. If we run this, everything should be running the same as it was before. Okay, great, so that's compiling fine. Now we're going to go in and we're going to add something from that clock and reset utility. It's called a clock and reset fixture. And there's a macro for that called clock and reset fixture. And this is a parameterized macro that takes 2 inputs. The first input is the half period for the clock in time units, so we'll have 5. And then there is a reset length. We're just going to put 11 here. So anytime you hit a reset, this is going to go into reset for 11 clock cycles, then come out of reset. So now we've got a clock and reset fixture. And now we have access to 2 different methods. One is called reset. 3 different methods, pardon me. One is called reset, one is called step for the clock, and then one is called next sample point, which is going to take us to a safe time off of the positive clock edge where we know that any outputs are we're going to be able to sample any outputs safely without any race conditions. So with our clock and reset fixture in place, we're going to go down and write a couple of more unit tests. we're going to write a unit test called QAB output is 1. And the way that test is going to start is we are going to do a reset. So this is a function that comes in that clock and reset fixture. Then, like before, we are going to set our A input and our B input to 1. But now instead of checking the value right away, which would be the asynchronous output, we need to wait for a clock edge for A and B to propagate to the output of the flop. Now a clock edge, we go to the next clock edge by calling a function called step. And step also comes from that clock and reset fixture. And this is basically just saying, wherever we are now, take me to the next positive edge of the clock. Now, on that positive edge of the clock, if we were to check the output, there's a potential for a race condition. And because of that possible race condition, we're going to call a second function called next sample point. And this doesn't do anything fancy other than just take us off of that positive edge to a point again where the output of that flop is settled on the proper value. There isn't going to be any race condition. So now if we sample the output of QAB, we can be pretty confident that the output is going to equal 1 as we expect. Let's finish that test. So again, let's go through this. So we're testing the output of the QAB flop. Because this is a synchronous output, we want to hit a reset first. This is going to reset the output of that flip-flop. There we're going to set our inputs A and B. We're going to set them both to 1. We're going to use this function called step from our clock and reset fixture to go to the next positive clock edge. That's where the A and B will be clocked to the output. And now we don't want to sample it right at that point because we want to avoid any kind of race conditions. So we're going to call a second function called next sample point. That will take us off the positive edge so that on line 95 we can sample our QAB output and make sure that it is equal to 1 as we expect. Now before we run this test, we want to make sure, one thing that I commonly forget to do is to make sure that the clock and reset are actually connected to my unit under test. And no, they aren't. So line 21, we have the inputs and the outputs, the AB and the AB QAB IO connected, but we don't have the clock and the reset connected. And I have made that mistake more than once. So we are going to add the clock and reset. I can't remember what those are called. I think they're called CLK and RST_N. Let's just go and make sure that that's right. Yes, there's our design. Got the right names there. So let's run this, and now we're hoping for a third passing test, and we have that. So we have our two asynchronous, or the synchronous output checked in the first two tests, and now we have a third test with the QAB output is 1. That's the test that we just added. Now we've got 3 of 3 tests passing. So everything is working out as we expected here. So let's go in and add one more test just to finish things off. We'll go back down here. We're going to test the false condition now. And oops. Copy this test. And we'll do a QAB output is 0. And what did we set our AB inputs to last time? So last time we set the A to 0 and B to 1. Let's do the opposite this time. Let's set A equals 1 and B equals 0. Whoop, I had a step 3 in there. We're just going to step 1. The last one we had a step 3 as well. We just need to step 1. 1 is the default value for step. And we're going to go to next sample point again, but this time it's not going to be true. It's going to be a 0, because 1 and 0 is 0. So there's our second test for the flopped output. We'll run this, and now we should have 4 of 4 test passing. Yes, we do. So our AND gate is working as we expect. The flop is connected and working as we expect. So at this point, our unit under test, our RTL, is working as we expect. Now there's one more test that we can add here, a useful test, and that can be that the reset state of the flop is as we hope, which in this case is 0. So we're going to write another test called reset state, test end, and in reset state we're going to manually control the reset. So we're going to set reset to 0. We're going to go to a next sample point, which again just takes us off of the positive edge of the clock. And we're going to fail if our QAB output is not equal to 0, because that's what our reset, the reset value of the reset output of the flop should be 0. So that's just a catch-all reset test. We can run this, and now hopefully we've got 5 of 5 tests passing, and everything's great. So that's about it now. So if you are a design engineer, I think that should be just about everything you need to get through the first few common hurdles of using SVUnit. We looked at how to build a unit test template there with create unit test. We set up some file lists. We set up a file list with some dependencies and some plus include directories. We did some unit tests for some combinational logic, which is actually a pretty handy place to start. And then we did another test, another couple of tests that verified some synchronous logic. So the output of a flop, and then of course the reset state of the flop. Now, if you want to run the code that we went through here, you can find it in the SVUnit download package under examples, modules, clock and reset. All of this code is there. You can load it and run it. If you go to agilesoc.com/SVUnit, you'll find some other handy reference material, notably the Getting Started page that will tell you how to download SVUnit and set up environment variables. There's also the user guide on there that goes through all the features and functionality of SVUnit. With that, I will leave you to get started with testing your own code with SVUnit. I'm Neil Johnson of agilesoc.com, and I will see you next time.